Okay, so that was objects on an incline. Would you believe that objects on an incline could be attached to objects on pulleys? Oh my gosh. So let's level this up. One more level, okay? We'll give some information though, okay? So I think that this description doesn't really give us a lot of info. Let's just toss it in, not like it's a storytelling, but just a bunch of givens, okay? So I've got object 1. Let's let object 1 be my dangling mass. And I've got object 2, that's my drag up the hill mass. And I don't know if you want to, like, in your own imagination, have a story for this. These are people trying to drag things to the top of a pyramid to do a construction job for some fella who's going to die soon. So I don't know, like whatever. I don't know, that was an Egyptian scenario, I guess. But like, I don't know why we're doing this, but it actually is useful to have counterbalances to drag things uphill. That actually is a thing that people do. And they'll have these two masses that are of a similar mass to each other, and all you got to do is add a little bit of extra mass on there, and then you could pull down on one side. And if these masses are a little bit counterbalanced, I could even add mass to the hanging mass, like maybe this is a basket or something, and you can imagine that it would drag things uphill, and then once the thing is dragged to the top of the hill, I unload things from the basket, and then the sled slides back down the hill. Like, this is an actual device that people use. And if you go to our school library, we have a clock. I just rewound it yesterday. There's a pulley with a mass on one end, and I pulled the mass up to the top by pulling down on a tab, and slowly that mass is going to tick, 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 tick over the next 8 days, because it's an 8-day wind on that clock, and gravitational potential energy is going to drive that clock for the next 8 days. It's kind of neat. Go check it out. You'll see the hanging masses. It's not exactly like this. It's a gear system that's being driven rather than a ramp dragging system, but some similar ideas going on, right? I think that's kind of cool. Anyway, so these old machines have been useful for some time, is all I'm saying. So mass 2, 20 kilograms, 20.0 kilograms. Let's give ourselves some significant digits to play around with here. Let's say that we've got a coefficient of static friction, of 0.0200, no units, and coefficient of kinetic friction, of 0.0100. Notice it's less. We'll give ourselves an angle of incline, theta, it's marked right here on the diagram, 30.0 degrees. And we'll let mass 1 be equal to 30.0 kilograms. Now, it's not necessary for mass 1 to be a bigger mass than mass 2. I just want to ensure that it really goes, right? The only time when mass 1 always has to be bigger than mass 2 is when it's a vertically hanging pulley, like this one. Like if I have a vertically hanging pulley, then the heavier mass is going to win. In the case of a ramp, because of mechanical advantage due to inclined planes, mass 1 doesn't have to be as heavy as mass 2, assuming friction's low enough, right? So it looks like friction's pretty low on this one. Now for this one, in terms of the system, since mass 1 is greater than mass 2, I would predict that mass 1 is going to win this battle. But if I wanted to do more than just make like a hazy prediction, I would say I'm going to calculate FG1, and I'm going to calculate, would I calculate FG2 or something a little modified? Yeah?
Friction?
Yeah, I'd have to think about friction, and I'd have to think about FG parallel on 2. So friction and FG parallel on 2, that would be the driving and resistive force on this one. And I'd have to see if whatever the sum of those guys is beats FG1. That would be my true tug of war this time. It wouldn't just be two simple masses like in this situation, right? So let's set the stage here. We've got to say, well, let's just make the vague statement that it looks like FG1 is greater than FG2. Therefore, it tends to the right. But it shouldn't just be FG2, it should be FG2 parallel. And that's what I'm going to claim I think is true here. But let's just make sure that it is true. And assuming that I'm right, I'm going to say right is positive, left is negative. And if it turns out after my math that I'm wrong, I'll fix that. Okay, we'll switch it around. So we say FG1, mass 1 times acceleration due to gravity, subbing in my values, 30 kilograms, mass 1, times 9.81 meters per second squared. And I'm going to just blast through this one quickly. 294.3 newtons, and you can check my math on that one if you like. Please do, make sure that I got it right. And then if I check to verify that this statement was correct, I could say, okay, FG parallel acting on 2 would be FG2 times, remember, FG parallel is sine theta. We proved that in the previous one. I'm not going to prove it again. This is a formula that I would suggest that unless you want to be deriving it each time yourself with F patterns and Z patterns, memorize that one. Okay? It's not on the formula sheet. This is one that's useful to know. But you should know how we got it. It's not just mathematical. So G2 MAG times sine theta. And we sub in our values. And I'm going to, for the sake of space, I'm going to ask for a little bit of trust on this one. Can somebody verify for me that the answer is 98.1?
Sorry, which mass are we using?
Mass 2. Mass 2. So the 20 kilograms times 9.81 times sine of 30. 20 kilograms times 9.81 times sine of 30. 98.1? So for the sake of space, I'm going to say 98.1 newtons. And as I look at this, I say, oh well, my claim that FG1 was going to beat the FG parallel 2 in this tug of war seems correct. I mean, even independent of friction, at the very least, even if this thing didn't go anywhere, this one's still the bigger tugger, right? All right, so in terms of the reference frames, to the right is positive, left is negative. That means that FG parallel 2, because of reference frames, is a negative value. And FG1 is a positive value, because of the way we've defined our reference frames. And this is my thought pattern. And it's hard to code a thought pattern like that, because it's investigative, right? So FG perpendicular to would be FG2 times cosine theta. Again, worth memorizing, but if you want to see the evidence, you can look at the previous mini lesson. And then we got mass 2 AG times cos theta, sub in our values, and again, please check my work. I get 169.914 newtons on this one. And you guys check me out. Mass 2, 20 kilograms, times 9.81 times cos 30. Yeah? Nods of heads, thumbs up. All right, so we got 169.914 newtons is the FG perpendicular for mass 2. Now, if you really want to press this idea of reference frames, we could claim that on the ramp, there's a perpendicular positive and there's a perpendicular negative. There's a parallel positive would be up the ramp this time because we defined to the right as positive, and there's a parallel negative down the ramp this time. So if you really wanted to press the reference frames, we could say that that FG perpendicular 2 is a negative value, although we know that if we're using friction later on, we only just care about the magnitude, right? So I'm just drawing your attention to the fact that if I want to be like really nitpicky about reference frames, I'd have to think about that, but it doesn't matter because it disappears as an absolute value later anyway. And I can make a little if statement. And the reason I'd like to do this if statement, sort of an if-then statement, is I'd like to figure out if we overcome static friction. Because this FG perpendicular is going to yield a normal force, and I'd like to know if I'm going to overcome this thing. So if the driving forces, that is FG1 plus FG parallel 2, is greater than Fs, then ignore static friction. And use kinetic friction instead. Okay, so this kind of an if-then statement. It's just a way to work around the fact that sometimes static friction is going to stop us in our tracks, and we have to prove that we're not being stopped in our tracks. Reasonable if-then. Now, if we're going to make this if-then statement, then we should actually figure out what that sum of the driving external forces are, FG1 and FG parallel 2, and it looks like it's going to be FG1, and we could write plus FG parallel 2, but just remember it's going to be a negative value. So plus FG parallel 2. And when I sub in my values, just because we've already calculated it, 294.3 oh my goodness, 294.3 newtons minus 98.1 newtons. And again, only just because I did the math earlier, I get 196.2 newtons to the positive direction. Can you guys confirm? Some people are doing this with their head math maybe even. Does that work out? Okay. And it looks like in terms of the friction force, the static friction force that is, the magnitude of the normal force would be equal to the magnitude of Fg perpendicular to, remember magnitude is all I really care about, so that negative sign's irrelevant really. So I end up getting Fs equals 0.02, that's the mu s value, times Fn, which is that value that we calculated already, 169.914 newtons. And again, only just because I did it before, I get 3.398 newtons. And then by a landslide, is this thing moving? Yes, boy howdy is it moving, right? So like that guy is way bigger, this thing is not stuck, and so we get to proceed. I won't say like as usual, but we'll proceed recognizing that it's moving. So I can say, all right, well, I can calculate Fk. UK times F normal, acting on 2. And that was the 0.01 times F normal 2, which was the magnitude. I can put the magnitude lines on there if it makes us feel better. 169.14 newtons. And, you know, I have it written as 1/100th, so we're just moving the decimal place over 2, so we definitely could do this in our heads. 1.6914 newtons. And if we really want to press this, that friction force is acting against the motion, which in this case is downhill to the left. So we can apply a negative sign to it if we want to. Yes, sir?
In this second line, it's supposed to be 169.914.
Oh, you're right! 169 point, is it 914? It is too! 169, and that means I dropped out a 9 there, didn't I? That's better. So this is going to not sit well with me. I'll have to make it better. Thank you for catching that. 169.914. Thanks, Jake. All right. And we can make a little statement. The system moves. And we could make another inequality statement, but I don't think we need to. This one's like 100 times bigger than this one. Anyway, we could say the F net for this system is equal to, and we can just think about what all the external driving and resistant forces would be for this system. We just list them off. Fg parallel to is going to be working on this system. Fk acting on 2 is working on the system. I'm leaving blanks because I haven't decided on positive and negative signs yet. And then Fg1 is working on this system. And it seems to me that Fg1 is the only thing driving things in the positive direction. Notice that if I want to put in my negative signs at the construction of the formula stage of things, friction's working against me. Fg parallel 2 is working against me. So if this is the stage at which I want to insert my negative signs, those guys are negative. So negative 98.1 newtons, 1.69914 newtons. Fg1 was 294.3 newtons. And again, please check my work on this one. I get 194.5008 newtons. That seems like a weird decimal. Did I get it right? Evie?
Page up.
Oh, shucks. Page up. Did I get it? Jake, is that a thumbs up?
Yeah.
Or you just hope so?
Hope so.
You hope so? Did anybody actually do the math on this one? All right, next one. All right. So then we say, all right, what are we even trying to find here? Oh yeah, we're trying to find the acceleration of the system. Keep in mind though, when you find the acceleration of the system, it's not just the dangling mass, mass 1, and it's not just the mass on the incline, mass 2. We're talking about the mass of the entire system. So we've had this 194.5008 newtons divided by, really it's mass 1 plus mass 2. So 20 plus 30 kilograms. Again, can you guys confirm I get an answer of 3.8900 meters per second squared? Yeah? And of course, all of that was 3 sig figs, so thank goodness, 3.89 meters per second squared. Up the ramp or down the ramp? Look, up the ramp, right? But the mass that's dangling is just going straight down. So since there's two objects and it's a system going around the corner, we would say that it's to the right. Otherwise, it's too complicated to talk about what one object is doing and what the other object is doing, since this is a rigid system bound together going around a corner, right? Now, the follow-up question to this one seems like a logical one, and it's not stated up at the, oh, it is stated up at the top. Up at the top, it says find the tension in the rope as well. Now, what I'm not going to do is I don't have time or space to do the tension portion of this and the generalized equation. Of course, yes, we could go back and we could construct an F-net sys generalized statement in the numerator, and the denominator would just be m1 plus m2. So if you wanted to go back and like backwards see if you can construct that for yourself, you're welcome to show me afterwards. We can look at it. But it's not going to be hard. Don't forget though, when you do it, make sure that you expand out to have all the stuff that's under the hood. Like FG parallel 2 has things hidden under the hood. FK has things hidden under the hood. FG1 has an M1 times AG hidden underneath of it. Like unbury everything. Like really leave all the variables in there, right? And even see if the masses will cancel it. Check to see if they'll cancel it. Maybe they will, maybe they won't. Check for yourself, okay? Now I want to take a look at this part. I'm going to call it part B, because all of that is what I would call part A. I know it's not stated that way at the top, but up at the top it says, and the tension in the rope. So now you say, well, oh nuts. I got to tackle this thing as an FBD, two separate objects. And if I think about these two separate objects, the one on the incline and the one that's just dangling, I know that there's, remember this is object 2, this is object 1. I'd have F normal 2, I'd have FG perpendicular 2, I'd have force of 1 acting up on 2, I'd have FK acting down on 2, or down the ramp that is. I'd have force of 2 acting up on 1, and force of G acting down on 1. And if I want to find the tension force, really and truly, I only have to find either force of 2 on 1 or force of 1 on 2. And I'm going to give you the answer, but I want to set up the expression, okay? So for this one here, notice that the perpendicular forces aren't necessarily going to be directly connected to what's going on in the horizontal, although I recognize that Fk and F normal are connected. So I can write F net acting on 2 is going to be force of K acting on 2 plus force of 1 acting on 2. Recognizing that at some point I'm going to have to put a negative sign in for that force of K acting on 2. Because the negative is going to be this way, the positive is going to be this way. For this object, the negative is going to be this way, the positive is going to be this way. F net for object 1 is going to be Fg acting on 1 plus force of 2 acting on 1. And again, recognize that just like Fk2 was negative, force of 2 acting on 1 is negative. Now, how do I know mass net for 2? Well, mass net for 2 would be mass 2 times the acceleration of the system. We just calculated the acceleration of the system down bottom left here. Yep.
For the first one, for FNet 2, don't you have to think about FG parallel?
Oh, you're right. How did I skip FG parallel? You're right. FG parallel 2. And that one's also going to be negative, isn't it? Yep. That guy's also going to be negative. So that mass 2 times the acceleration of the system is going to be the negative of the FK2 plus force of 1 acting on 2 minus FG parallel acting on 2. And I'm going to put a box around that. My other equation, as I said, is going to be mass 1 times the acceleration of the system equals FG1 minus force of 2 acting on 1. I'll put a box around that. And if you like, this is my equation 1 and this is my equation 2. We have enough information to solve for force of 1 acting on 2 or force of 2 acting on 1 with what we have already. And I want to challenge you to do it. Take a minute to do it. Now I'm going to tell you what the answer is so you'll get that like immediate like lucky feeling once you get it. If you get an answer of 178 newtons, you should have a good lucky feeling, okay? We'll leave it at that.